Okay. So this is question 34 from chapter 28. And here we are given a strange shaped loop, a current carrying loop. So this is a circular arc and a bigger circular arc. In fact, these are arcs of two concentric circles of radii R1 and R2. Okay, like so. These are circular arcs and these are the radial segments. So our current is flowing this way on this loop. Some current I is flowing, and we are required to find the magnetic field at this point C. This angle theta is also given, and we are required to find it, of course, in terms of this theta, this current R1 and R2. Okay. I believe that's all. Okay. So this is an application of Biot-Savart law. It's kind of shouting Biot-Savart, but so let's write down Biot-Savart law. So this is law that says the magnetic field given by a small segment of current is going to be given by this formula. Okay. So what this formula tells us immediately is that these two radial segments are not going to contribute to my magnetic field at the center of these circular arcs. That's because my R for those points is going to look like this, and my dl is also going to look like that. When dl and R are parallel or anti-parallel to each other, the cross product is going to vanish, so no contribution from these two parts. Okay. Now for these parts, the R, let's say that I choose some dl over here, so it's going to look like this. Imagine that this is infinitesimal, and my R is going to look like this. So for this inner circular arc, dl and R is going to be perpendicular to each other. Right? And of course the same goes for the outer circle. Now why is this so? Well, this dl is an infinitesimal part of this circular arc. So in some sense, if I extended this, it will become a tangent. Right? And of course, for a circle, the tangent is going to be perpendicular to the line segment that connects the point to the center of the circle. Right? So the radial direction and the tangential direction are going to be perpendicular to each other. And this is correct for every point on both of these circular arcs, which means that this cross product is going to become a simple product. Right? So the cross product involves a sine theta factor, but sine theta in this case is sine 90, which is just 1. All right, so I'm going to call these segments 1 and 2 and calculate the magnetic field produced by both of these segments. So let's start with 1. So first of all, I'm going to find the direction of this magnetic field. So this dl is this way and R is that way, so is R head. The actual vector in our formula. So that is going to be towards us. So the magnetic field of the first segment, B1, is going to be towards us. And the second one is going to be the opposite direction. Okay. Okay, so these are both at the center. I'm drawing them off center, of course, but they're both referring to the magnetic field at the center. So what will be the magnitude of B1? Now I need to take this and integrate this, and because the magnetic field produced by each little segment is in the same direction, namely pointing away from the blackboard, I can actually write that actual vector sum, this one, as a scalar sum. Because they're all in the same direction, I don't need to deal with the vectors. Okay, then I can write this right away. So this is mu naught 4 pi r square I. Now that dl is just dl, and this r head becomes the magnitude of r head, which is just 1. Okay, so this drops out. Okay, so the cross product becomes a simple product of the magnitudes. The magnitude of dl vector is just dl. The magnitude of r head is just 1, so it just goes away. Right? Forget about this. And this is a constant. This is a constant. This r is the distance of the line segment from the center. It is also a constant. It's just r1, so I can take that out. The current is a constant, and I end up with dl. Okay, so mu naught I over 4 pi r1 square integral of dl. And this integral is taken over this inner circular arc. Okay, now, if this was a complete circle, then it will be 2 pi times r1. Because it's a circular arc of extension theta, it's just going to be, instead of 2 pi, we have theta. So theta times r1. So mu naught I theta r1 over 4 pi r1 square, and these partially cancel. We end up with theta naught, mu naught I theta over 4 pi r1. Okay? And this is going to be pointing towards us. Well, everything we do for B1 also goes for the second segment for B2. So B2 is going to look pretty much the same, except I'm going to replace 1 with 2, 4 pi r2 I and theta, and I need to take their difference to find the net magnetic field, because this is going to be they are going to be in the opposite direction. Now, R1 is a smaller number than R2, so its reciprocal is going to be larger. So the magnitude is going to be B1 minus B2. That's going to be a positive number. So let's write it that way. So B magnitude is mu naught I theta over 4 pi 1 over R1 minus 1 over R2. This is the magnitude, and it's towards us. Okay? Out of page. That is the direction. They are not giving you any coordinate system in the book, but you could, of course, invent one. No. X, Y, and Z. Then instead of out of page, you could just put K hat. Right. That also works. But this is also perfectly adequate.